AI number 3. Today, I'm excited to do a dry run of the first session of an in-person bootcamp that we're organizing, and we'll likely do this a few times virtually as well. Of course, everything here is going to be on YouTube and eventually on the podcast platforms. Just as a reminder, I'm going to try to explain things verbally in a way that even though I have some diagrams and pictures on the deck that I'm sharing, the goal is that if you're just walking around and either listening to YouTube, I do that a lot, or iTunes later on, you'll be able to get the gist of what we're talking about. Okay. Now, let me know if you can see the screen.
You can see it.
Great. Yeah, so today we're going to look at some foundational knowledge, some fundamentals of LLM. This talk could probably be given over the course of 2 to 3 hours, and going even deeper in terms of how the deep learning works, and the gist of machine learning. You could go even deeper than that. So I'm not going to go into that much depth. I think it's the right amount for software engineers and data engineers to just get an idea of what they're dealing with. I was telling somebody, most people that want to use the LLM technologies, it's like they want to make an app for their iPhone. They don't care how the microprocessor works on the iPhone, right? They don't necessarily care what the operating system is built on. They just care that it works. And same thing, if you're making a website, right? You don't really care too much about Chrome or Edge these days. They're actually all the same engine. You just care that it works. And so I have the same thought about LLMs. As long as they work well, I don't really want to go dig too much deeper. Although in some cases, fine-tuning an LLM, and we'll talk a little bit about what that means, may require some more machine learning knowledge. I think LLM ops, ML ops knowledge. But for most people, LLMs are an API, right? So let's just understand what they are and go from there. So, for folks that are not in technology, actually, I would say like most people that are working in business have experience with technology in one way or form. But for people that don't make technology, people that don't program, LLMs seem like magic, right? It's like an Arthur C. Clarke quote: any technology sufficiently advanced is like magic to somebody, right? It's something like that. But in computing, when you understand what it does, I think LLMs show a great promise in kind of bridging the gap between a human and a computer. So far, over the last 25 years or so, I've been in this industry, primarily working on internet applications. The way that we work with a computer is using a browser or our phones, and it's an app. It's a graphical user interface. Some of us are comfortable with a command line interface. And now we're entering into a world where there's a concept of a language user interface, because that's what LLMs can afford us. They can give us an opportunity to talk to the computer as if we were talking to a person. And I think that's really where the promise is being able to take that bridge between a person talking to a computer as if they were a human being, and then the computer taking that and doing something with it on behalf of the person, on behalf of the user. Shameless plug. I work for a company called Anant. We do some radically cool stuff at large scale for the brands we work with. We do real-time data platforms, analytics, the machine learning, and connecting it to various parts of the business platform, whether it's customer experience, info systems, CRM, so on and so forth. Another plug for the bootcamp that I'm organizing. This session is actually going to be the first talk of the in-person bootcamp. This is a dry run. It's a LLM Inside bootcamp with with Cassandra, which is a big data database, and it's actually relatively easy to use if you use a Cassandra as a service. And the goal is to get people not only understanding what LLMs are, it'll go in depth in terms of the different design patterns. Ultimately, at the end of the day, people will build an application, a large-scale LLM application on top of Cassandra with obviously OpenAI is probably the LLM we're going to use. And then other software that has come out in the open source frameworks, such as LangChain or Llama Index. And person will walk away with an application that, you know, they can put terabytes of data into if they want, and essentially be able to talk to it as like GPT, but with their data. The agenda for the bootcamp is in 4 parts: strategy and theory. There's a little bit of overlap in what we're talking about right here with that. Design patterns, as I mentioned, there are different types of language user interface design patterns. There's also design patterns for how you get data in and how you get data out. We'll showcase and walk through 3 stacks: no code stack using Bubble with OpenAI. We'll have a stack that's full code using Python, and likely a React app talking to OpenAI with your own data. And then we'll look at an enterprise implementation where the data can't leave the environment. It can't leave the enterprise's virtual private cloud. So how do we implement an LLM if we can't directly talk to OpenAI? So there's some patterns we can employ. And then we will walk away with an application at the end of the day. Today's agenda is fundamentals of LM and machine learning, the transformers architecture, which is the main innovation that has allowed for us to have LLMs these days, how the LLMs work. Again, I've learned some stuff from other people. I've thought about it in a particular way, so this is my explanation for how they work. And then LLMs other than ChatGPT or GPT. If you're starting out, you're likely going to be using OpenAI's API, but there are contenders, and you'll find it interesting that companies like Google are scared, and you'll understand why in a moment. We're going to talk a little bit about the history of LLMs. This is a bit of a repeat from the Monday session on Data Engineers Lunch, but I think it's worth repeating. What is machine learning and AI? If you're not familiar with what machine learning is, a quick deck to show what it means for folks. And then the transformer architecture, we'll talk a little bit about how it works. But we're not going to go deeper into what the code looks like. There's lots of other talks on YouTube. There's a great GitHub and Jupyter notebook, GitHub repos and Jupyter notebooks that you can get on Google Colab to do this. We're not going to go into that depth. So I would say the history of LLMs and AI will probably be measured in a before ChatGPT and after ChatGPT, because before ChatGPT came out for normal people to use and talk to in late 2022, the long history, as you can see from 1950s and 60s, there were just incremental improvements, and in this timeline, it's from about 1965 for natural language models. Before that, people were doing other types of machine learning as early as the 40s. And here we are in 2015, where OpenAI was founded, right? And then between 2015 and 2022, lots of stuff has happened. And this timeline is made by somebody else, and it's not always kept up to date, but I would say more has happened in the last 6 months that has probably happened in the last 6 years or 7 years, and it's just there's so much to talk about that we really can't talk about everything. We can just talk about it in broad terms. And now everybody wants to know the party, right? So if you're thinking you're late to the party, don't worry about it. You know, this whole craft of engineering with LLMs is only about 6 months old, if that. You know, at the end of this month, it'll be 6 months old. So it's maybe 5 months old. So don't worry about it. You're right on time. Machine learning in a nutshell. If you haven't seen this kind of flow, I think it's worth explaining to everybody that the difference between machine learning and traditional programming is that in traditional programming, we give data and we give it our program, what we wrote, our algorithm, which is a step-by-step instruction set for what to do with the data. And then there's an output that comes out of it. And that fundamental formula is used all throughout the stack, at the operating system level, the database, the software layer, the user interface layer. Ultimately, it comes down to data going in, there's some code that processes it, and then does something with it and sends it back to you. In machine learning, we give it data and we give it what the expected output should be, and that's also data. But that's the training data, right? And the only way, and the computer basically makes the program for us. So the more data we give it, and the more training data we give it, in general, the better it's going to get. And so you may say, well, that's pretty simple. Why hasn't this simple formula, you know, gotten us returns like the ones we have now? Well, we'll get into that. But ultimately, the only way to improve a traditional program is to improve your code and write more rules, if then, switch statements, etc. In machine learning, you write more, you know, you can improve the architecture of the machine learning system, which we'll talk about in a second, and that's what the transformers architecture is. But ultimately, it's more data equals better quality. And there's different types of learning: unsupervised, supervised, and you know, the balance between the two is really what has been making the big difference. The other thing to take away from machine learning is that most of the technology that you use that people say is machine learning or AI is built on neural network technology. Neural networks have been around since the 40s. It's a concept taken from how the brain works, and it's not the same thing. It's just there's neural network, and what's in your brain is called a neuronal network, because in your brain you have neurons. But an artificial neural network, also known as ANNs, basically they process information through a network of these nodes that have a number attached to them, and then they have basically a bias attached to them. There's weights and biases basically, and the weights and biases in a network of neural networks is what produces basically this program. So you give it a lot of data and it comes out with what the values of this neural network should be, and that becomes the model. How these neural networks improve is we keep feeding it data, we keep testing it to see how good predictions are based on our training data, and we try to minimize this loss, meaning you know, the difference between what is expected and what's being given back. It's not always going to be 100%. And we go back and we try again. So this is a loop. This is kind of the backpropagational neural network process. And you know, I was doing this stuff in high school nearly 24, 25 years ago. And the same technology roughly is being used today. It's just the difference is the way we can implement it today and the scale we can implement it today is what makes it possible to do what we're doing today. So what can neural networks do? Well, they can recognize a bird. It's like that. I think it's Silicon Valley show. You know, it's like there was a kind of a farce app that they made. It's called, you know, Hot Dog or Not Hot Dog. And essentially, the way it can detect if it's a hot dog or not a hot dog is that different layers of the neural network can detect different parts. So, for example, it can, in this facial recognition, what it can do is it can first detect features of a face, such as different curves. Then it's able to, it's able to understand where there's contrast. So like, what's behind me is different than what contrast is on my face. Then it can detect my facial features, and then it can detect a face. Okay, but all neural networks are basically, at the fundamental core code, it's basically numbers in a matrix. That's essentially what a neural network is. It's the numbers, the weights and biases in a matrix, which is a data type in programming. And we do tons and tons of matrix mathematics multiplication to get the next improvement the passing of the data through the model is basically matrix multiplication. So how does it know what this is? Well, this picture is broken up into different pixels, and those pixels have values. And because we train it to say things that look like this are a bird, over time it starts to detect the features of a bird, and it can say this is most likely a bird. Okay. Speech recognition, another one. There's lots of great stuff now happening in video. And then initially, up until I would say 4 or 5 years ago, most of the ML stuff we were looking at were given this, detect what it is. Given this MP3 file, detect what the words are. And recently, the new kind of AI that people are experiencing and playing around with, it's called generative AI, which is given an input, it can start to predict new things, not necessarily what you had given it as a right answer. And that's generative AI. So stable diffusion, Midjourney, these are different text to image models. GPT-4, these are text to text models. You give it text and it creates text for you. There are some video models coming out where you give it text and it has a little video, or a 3D model where you describe something and it creates a 3D model that could be put into, let's say, an AutoCAD or a game. So generative AI is relatively new. It's still based on the same fundamental architecture using neural networks. The more data you give it, the better they get. The more layers you have in a neural network, the better they get. And so, this is something I heard at a training on deep learning, is that you don't really have to think too much these days about how to, improve your architecture, because, with the transformers architecture, it works pretty well. You just have to add more layers, add more data, and you will get something pretty decent. And that's an overgeneralization. So what's the big deal about transformers? Well, they weren't invented by Elon Musk. And because ANNs are implementations in matrix math, and that relates to the matrix of leadership, which is what Optimus Prime has. No, that's not the reason why they're called transformers. Transformers, they take data, they decode, they encode and they decode data into tokens, and essentially that architecture. And I'm not going to go into this. I mean, there are definitely people better that can explain this. But this architecture is what allows a sequence of words to be converted into tokens, and then the sequence that comes after it comes from the decoder, after the fact. This architecture also does well when there's a lot of data coming in, like a lot of text that's coming in. It's able to break it down and basically predict the next word and predict the next word and predict the next word. And you'll understand what I mean by that in a second. And actually, I should also edit this. Transformers are not a hardware accelerator that speeds up AI computations by several orders of magnitude. That's also wrong. Should have crossed that out. So how LLMs work and what they do, we're going to go deeper into transformers architecture, and then we'll talk about ways to explain what an LLM is and how it works. Hopefully one of my explanations will stick, and the best way that I would say you can understand that you understand it is by explaining it to somebody else and seeing if they understand it. I don't know if that makes sense. So how does a large language work? So the transformer architecture, it has an encoder and a decoder. And when you give it a sequence of words, it creates these embeddings, which are numbers. And there's a thing called self-attention, which is it pays attention to the words coming right behind it, right? It's not predicting the next word after what I'm giving it. It's actually taking a look at the sequence of words behind it. And there's a paper called Attention is All You Need, and that is what the transformers architecture comes from. Now, the decoder takes it and creates an output sequence based on what the encoder has given. And again, also using self-attention to try to get the most likely word that's going to come out in that from that input sequence, what's the most likely word or token that's going to come after it. And when you put these things together and you have tons and tons of data, and then you add to that what's called reinforced human reinforced learning, it gives the model not only all this data and how to predict it, but also what a human would expect, right? And that's ultimately what is the big difference between before, when we had GPT-2 and GPT-3 and GPT-4, was that there was more and more human input to say, hey, this is a better answer. So what do? Essentially, they predict words, right? So if this is a sequence of words, after the game we went, there's a likely word that comes out, and there's a better word, like let's say home, right? We went home rather than after the game we went eating. Now that's pretty good as well. Or after the game we went hiking, that's pretty good as well, right? But after the game we went mouse doesn't make sense, so that there's a much less probability that that's the word that's going to be sent back. And this is an embedding inside the model. So these words, they get embedded with a number, and then these numbers go through the sequence, the decoder and the encoder, and the next word is created. And then this whole thing is sent again, and then again, and again. And that's what looks like magic when you start asking a question in ChatGPT and goes, that's what it's doing. It's just, it keeps repeating, right? Going and saying, what's the next word likely for after the game we went home, then what would be the next word after that? So the positions do matter, right? There's a difference between the walked chicken and the chicken walked. And that's the self-attention that can help us get to the chicken walk across the road, right? And this is what it's doing. It's a word predictor. How does it know what to predict next? What is the data that was used to train all this? Well, it's coming from the outside world. There's what's called the Common Crawl news. Common Crawl is a big open source data set, which is the crawled internet saved onto a big hard drive. And you can download it if you have the hard disk space, and you can process it, and you can do stuff. There's the pile, which has a bunch of stuff from various, I think, news sites and like Reddit and things like that. There's the book corpus, meaning all the books that are in the public domain. I don't know what push shift is, but I guess they get social media data from there. And then there's another data set called the C4, which is the Common Crawl cleaned content, I guess, C4. So the data that's being used, at least in the open source world, it's all out there, right? If you wanted to train your own model, you have the machinery, the computing power, the money, the GPUs, the TPUs, or whatever to do it, you can do it. I would recommend you don't do it. You probably don't need to. And that information goes through and it creates what's called a generative pre-trained transformer model. That's where the word GPT comes from. Generative pre-trained transformer. What can you do with this word predictor? You can make applications that have natural language translation. You can say, translate this to French. You can have chatbots, which is basically what made it all famous with ChatGPT. You can use it for content creation. So lots of companies were using the GPT-3 API before ChatGPT came out, which was probably using GPT 3.5. So Jasper, Writer, a lot of apps out there, they started saying, hey, we can write blog posts for you. Well, that's what it was powered by, right? These companies didn't make that technology. They just connected it and put a user interface in front of it. You can do the same thing. So here's another way I would explain that what LLMs do. They narrow possibilities. So when you have a request, a set of words, it's taking all of the things that could come back to you, right? So technically the machine can just send you random characters, right? And that I would say is chaos, random characters and random numbers. But it doesn't do that. It gives you something back in English. So there's another smaller possibility of what I would say garbage in English, meaning it can respond to you in English, but it doesn't make sense in terms of the answer that you get back, right? So as the models got better and better, they take the probable responses in the let's say a particular language in English, and as you give it words, it narrows down the probable responses, right? And in this world, there's a bunch of responses that make sense in terms of they're in English, but they don't make sense. There are responses that do make sense. And then there are responses that make sense for you. So the better you give it an input, the better prompt you give it, the better document you get back. And every word you add to your prompt basically reduces the universe of what can come back to you. We'll talk about universe in a second. If you give it one word, it'll give you something back. If you give it 20 words, it will give you something back from a smaller possibility, because every token that gets added to your prompt is basically narrowing down from, and almost, I wouldn't say infinite, there's a finite number of things that can come back to you in English, and it's giving you some small portion of that, that multiverse. This is something that I'm, taking from the full stack deep learning guys. They say, what do LLMs do? They do verse jumping. And verse jumping meaning, if you've ever seen that movie, Everything Everywhere All at Once, if they do some weird stuff like eat chapstick, they can like jump a universe. But essentially, there is in the LLM various possibilities of documents. They're all there, and these collections of these words are what I would call a document, right? And inside the LLM, it doesn't look like English. It's actually just a series of numbers that represent these tokens, right? So this is from the GPT-4 token verse. I just downloaded it from GitHub earlier today. And as you can see, the very first token are like exclamation mark, double quote, and then down the line here, there's randomly a string of asterisks. There's a space and a chicken. There's programming, terms in here. So this doesn't make sense to you, but to the computer, the token versus the possible tokens that could be put together, right? And so it doesn't really represent what you give it on a word by word basis. What it does is it breaks it down into specific tokens. And so, for example, Win and Windows are two different tokens because they mean two different things. And as you give it more words in your prompt, the universe of documents, meaning sets of tokens together, reduces, because technically anything is possible if you don't give it anything at all. And what does that look like a little bit more tangibly? So let's say that this token verse here, 1 through, I don't know, there's about 100,000 in there. So let's say this is token number 1 and this is token number 100,000, right? This is one big pile of tokens. When you give a word, your first word may be this position in the array of tokens. The next word may be up here, the next word may be up here. And this sequence of numbers, where it is in the token dictionary, 1, 2, 3, 4, let's say 4 tokens, we'll just call that A prime. That's our prompt. That's what we give it. But because we gave it these tokens, it's more likely to produce this set of tokens together. And this sequence of tokens together is your document. And if you give it different tokens, different prompt, you're going to get a different document. There really shouldn't be a number 4 here. And the more words you give it, the quality of your prompt actually helps create better and better documents. And I'm saying it creates it, but really it's in there somewhere in the model. It just picks these words up, predicts the next one, predicts the next one, predicts the next one, and it comes out looking like English to you, looking like there's a human behind the scenes, when reality is it's predicting words. The scary thing is that people don't know why it works so well. They don't understand how just a bunch of data going through this neural network gives it the ability to seem like it can reason. And we'll cover that in a different talk on prompt engineering. But it's pretty capable. There are lots of other LLMs available. ChatGPT, GPT 3.5 Turbo, GPT-4 if you have access. They're not the only ones out there. There are now many, many different LLMs. There's projects by the hundreds, I would say at this point. I was going to say dozens, but it seems like there's a new one coming out every week. There are commercially available ones that they just take care of it and you call an API, just like you would talk to OpenAPI's GPT. There are also open source ones available, and we'll take a look at how they were trained, or tuned rather, and then we'll just do a brief review of what the cloud providers are. So popular public LLMs. So OpenAI is probably the most popular one. It's available. It's easy to get access to. You have to get on the waiting list for GPT-4, but it's all there. I know plenty of people that have access to it. Anthropic is the company that is behind the model that powers Poe, which is Quora's app. It's a pretty good app, actually. And actually, Poe added other models, including GPT, in there, so you can actually try them out to see which one is better. But the API from Anthropic is available, and when I talk about the private cloud stuff, you can also use it through Amazon Bedrock. Cohere has a baseline model that competes with OpenAI's GPT model. GPT allowed you to give it your own data to train it, although I don't think they're doing that anymore. Whereas Cohere still allows you to do that. So you have your base model that you can use to do similar things like what OpenAI can do for you. But then you can also give it a bunch of data that you have and say, hey, this is my data. Here are my questions. Here are my answers. Here are my prompts. Here are the responses. Go to town. So before I talk about the open source models that are out there, I wanted to bring attention to an article that got published not too long ago, I think last week. And it was a leaked paper or memo from inside Google. It was leaked 6 days ago, so less than a week ago. And it basically explains to people in Google that they have no defense, they have no moat against what is happening in the large language model space, that anybody can create models now that are really, really, really good, right? So we'll talk about Llama and Alpaca in a moment. And basically, I'm going to actually update this so that you can actually, there's a, that's the one that should have been there. So what this explains is that within 2 weeks of the Llama model that came out from Meta, Alpaca came out from Stanford, that they fine-tuned it, and we'll talk about fine-tuning in a second. And then a week after that, Vicuna came out, and Vicuna is at 92% performance rating compared to ChatGPT. It's the one that you use on the app. And ChatGPT is pretty good, right? And Bard from Google, the one that they have put out there, which is not that great, is 93% as good. So the open model, Vicuna model, is almost as good as the one that Google is putting out there. Now, that's a laugh. That's just like that's a shameful thing. If I was working in Google, I'd be so ashamed, right? And so what the paper talks about is what happened and what's important. And this is important for, I think, everybody to understand, not just Google. It's what happened. So Meta open sourced this Llama model. They said that you can't use it for commercial purposes, and there's other ones that you can, but let's just focus on Llama for a second. GPT answers were used to train it. So they used GPT to get high quality questions and answers, and then they used it to fine tune it. They used a technology called low rank adaptation. And so normally when you pre-train models, it takes lots and lots of data, lots and lots of computation. But when you have an existing model and you have fine-tuned data, you can reduce the number of parameters essentially to get pretty good results. And this is what the game changer is that the cost of training this is like $500. The cost of training this is like $140, right? And so retraining models, huge models with more and more data, like all of the data, is extremely hard. And iterating on small models by continuing to fine tune them it's better and it's cheaper, and it actually gets pretty good. As you can see, you take a model that was only 70% as good as ChatGPT, and you give it fine-tuned data, and you can have it to be, be as 92% as good. And this is only going to get better. And the way it gets better is by having better quality of data, right? So having more quality data than the amount of data, the quantity of data, is what makes these things better. Remember when we were talking about machine learning? Good data, training data is what makes the machine learning model better. The same applies here. But in this case, the quality really does matter. You just don't want to put the whole internet in there when you're fine-tuning. You want to fine-tune it with what you have as knowledge. Battling open source means failure, because when Meta/Facebook open source Llama, they basically had the whole world take it and start using it. Even though it was for non-commercial purposes, lots of researchers started to play with it. And now we have something called stable Vicuna, which you can use for commercial purposes. You have something like Dolly 2.0, which you can use for commercial purposes. So people learn, and the biggest thing is that Facebook can see what these people are doing and put it back into their closed system if they wanted to. The companies need users and researchers more than the researchers need the companies. Individuals can use different licenses. So, as I've said, lots of researchers, lots of people that were tinkering with it, they were able to do cool stuff, and they get good fame and notoriety for doing it. They don't necessarily get paid for it, but now they know how to fine-tune a model, right? And you can do it too. Being your own customer is the best way to really get good at this stuff. So these people that are playing around with these models, they're using their data and they're understanding how to fine-tune it. So just because Google has a whole internet doesn't necessarily mean that their model is going to be better for you. It's you and your use case and your data that's going to make it better. Let open source do the work, right? So they basically telling Google, put your stuff out there. Don't try to control it. People will work on it. If it's good, they will give us feedback, and then we'll just have our model being used everywhere. And then the last thing it says is that OpenAI doesn't have a moat either, right? They don't have any defense against this either, because if in 3 weeks people can create something that's 92% as good, and then there's now models that are 90% as good as GPT-4, which is even better than ChatGPT. It doesn't really matter if you have OpenAI GPT-4. If you can tune your model and get decent performance and not have to pay OpenAI, why would you pay them, right? Because there's a cost to using the API. So how was the Stanford Alpaca model trained? They took data from OpenAI's Text DaVinci 03. This was the precursor to 3.5 Turbo. And they gave it certain questions, and it got a bunch of great answers back because this was a well-trained model. And they put basically 52,000 examples into the Llama model, and they got Alpaca 7B. So just to kind of remind you, this is Llama, and this is Alpaca 7B, almost a 10% improvement. Oh, sorry, 13B is actually better than that. So this was 7B and 7. This is just the number of parameters. So this had 7 billion parameters. That one has 13 billion parameters, meaning the number of neurons kind of coming into the neural network. And then Vicuna, they took the same general approach, and they took data from user shared conversations that people were putting out there. So if you go to shared GPT, people share their conversations that they're having, and they took really good ones from there, and they fed that, and they evaluate it using GPT-4, because GPT-4 is like magic. So they compare the output that they're getting from their model with what GPT-4 would give, and they ask GPT, say, hey, how good is this answer compared to what you gave it? And that's how they get these numbers of like how it's 90% as good or so on. Right. The main there's a site. So the people that released Vicuna, they have a site called chat.lynchs.org that has a leaderboard, and you can try out all of these models on there in a web user interface. Vicuna, Koala, and Open Assistance Pythia are like the most popular ones on there, and then Alpaca is like a close fourth, and then there's more. Stable LM is relatively new. That's a model from the stability folks. They created Stable Diffusion. They open sourced that Stable Diffusion image to text model. Text to image generative model. They released their language model now, and people are using it because, well, it can be used for a commercial application. So Stable LM, DALL-E, these both can be used for commercial purposes. And ChatGLM is relatively new. I talked about it on Monday, but basically it's trained with English and with Chinese, and Chinese is a big part of the internet. The cost of fine-tuning Alpaca and Vicuna is what really caught my attention. So, Llama, for example, cost, and I'll just do the math here. So what is 82,000 GPU hours, right? So comes out to be $2.40 per hour, right? So if we did the math, and I just got this off the internet, you can just like Google how much is a GPU hour. That's the amount of GPU processing. So 82,000 times $2.40, about $200,000 for this one, and it's roughly, I guess, twice, about $400,000 to train the better model here, right? And at this time, the 13B had not been trained. But it cost $500 to get the data from GPT, because it costs every time you ask it to get data, and about $100 to train it. And then Vicuna, which took from user shared conversations, meaning the ones that they liked, so even more human input there, it cost $140. And to do the better one, which is 13 billion parameters, $300. So why is this important that this cost is going down? And it only takes about a couple of hours to do it? Well, that means that as new data comes into your company, to your platform, you can retrain your model on a weekly basis, and it'll be better with your data, right? And it's not going to cost a fortune. And then as it gets even better and better, you could make models that are just specific to a particular business function, like sales, HR, marketing. And then if it gets cheaper and cheaper and cheaper, you could basically make models per customer, so that when your customer is talking to the company, the model can respond to it in a way that it's informed about it, or at the very least, a customer service person can talk to a model just for a customer, and they will have all the answers related to that customer, right? And there's different ways to do this. You don't have to do fine tuning to get that type of intelligence. Remember that the data in these base models is old data. It took the internet, as it was called until 2021 or 2022 to get it to be so good, right? It doesn't continuously update. That's why the cost of training is so expensive, because it has to take all that data. And going back to what the Google memo was talking about, in this case, they take a base model and they just train it with better data, and they keep training it and they keep training it. And that's the incremental improvements. So the promise of these open models is that eventually it's going to get so cheap that any business platform or technology platform worth its weight is going to have custom models, fine-tuned models eventually. And right now, I would say you don't have to do that. There's data augmented in context tuning that doesn't require any of this. You don't have to be a machine learning person to do in context tuning. In this, you kind of have to know some data ops, ML ops. It's a little bit of a heavier lift. There are public models available in case your company or organization cannot send data to the internet directly, like OpenAI's API. You can use Azure OpenAI in your virtual private cloud. So there's lots of companies and governments that run on Microsoft Azure. It's firewalled. They can rent a machine from Azure OpenAI that has the latest GPT model there, and your code, you change it to talk to a different endpoint. And you know that the data is not leaving your virtual private cloud, it's just going to that particular machine. Amazon Bedrock came out recently. Their offering has their own model, but it also offers the managed hosting of Claude from Anthropic, which we talked about earlier, and Stable LM amongst a bunch of other open ones. So that's probably a really good stopgap from you training your own model, is maybe using one of these options and then using their built-in ecosystem to do fine-tuning. Google has a way to train your own or fine-tune your own model, but it's not like as easy to use as OpenAI or Bedrock. And NVIDIA, I've looked into, looks pretty impressive. Again, they have some base models, but you have to fine-tune it for your needs. I had thought about going into the difference between, be more in depth and talk about the difference between training, tuning, and then what I call taming, which is using an existing model, not having any machine learning experience. How do you tame an existing model? And that's really through your own data. But I don't think I would have been able to do it justice. So in a next segment, I'll go through what it actually takes to train a model, why it's so expensive, fine-tuning. We'll walk through the steps of how do you create a Vicuna model yourself for your your business or your data. And then finally, we'll dig deep into taming existing models, which is the most realistic approach that people are going to use for a long while. For getting the large language model to do what you want. I usually do key takeaways, but the main takeaway I have for you is to just remember the history. Neural networks have been around since the 40s and 50s. TensorFlow, PyTorch came out in 2015, 2016. These were ready-to-use software that you could run on GPUs, on specialized hardware that could do parallel processing at scale and at relatively cheap cost. Like you don't have to have a supercomputer, you could just rent it on the cloud. And then you have transformers and the attention paper coming out. Transformers attention paper is the same one. So the attention paper coming out 2017. And when TPUs came out, these are tensor processing units from Google. It allowed companies to do even more advanced, larger deep learning models. And then you have GPT original, GPT-1, GPT-2, and then GPT-3 was out almost 3 years ago. So why haven't we been talking about it? Well, because GPT-3 would give you several answers back for a particular question. And then you could pick the best one. Or Instruct GPT, you would tell something and it started to be a little bit better, but it wasn't always great. And you could access this through API. That was the only way to access it. or if somebody had wrapped it with their software, like Jasper and Ryder. But in 2022, ChatGPT, powered by GPT 3.5, made it so easy for anybody to use and see what's possible that people really started to look back at the API and say, oh, the models are this good. How can we automate this? Right. And that's really the turning point. That's the last 5-6 months of everything that's happened is based on this turning point before ChatGPT and after ChatGPT. And everything between Q1 and Q2, which isn't even over yet, there continues to be lots and lots of innovation, right? So knowing that, don't be disheartened to say, oh, I'm kind of late to the game. No, everybody's, unless you're, got billions of dollars to do the R&D like Apple and Google and Microsoft, most of us are going to get access to this whenever we get access to it. But the time is now, right? We're still in the first 6 months of this whole movement. This is the time to get involved. So deep learning, big game changer. Transformers, big game changer. What are LLMs? Well, they're just good at predicting text, predicting the next word or the token from a token verse given some input. That's all it does. Given something, what's the next word? It takes it and then says, what's the next word? Then takes that, what's the next word, right? And the quality and characteristics of what you give it narrows down this document constructed just for you from a multiverse of documents. And that's why when people say, oh, it's going to take over the world, I'm like, dude, it can only handle 4,000 tokens or 3,500 words at a time, or it can only handle 32,000 words at a time. Beyond that, it has no. The reason you can talk to ChatGPT and have it kind of continue a conversation is that GPT is keeping track of your conversation and summarizing it and then sending it back and then summarizing it and sending it back. If you use ChatGPT for a while and you ask it, what's the first thing that I told you in a long conversation, you'll probably see that it forgot the very first thing that you gave it. It's not, going to take over the world, but, it may have a part in it. And the reason is because it makes it easier for a person to talk to a computer, and then that computer taking that instruction and doing something with it. And we'll cover more of this type of, the routing ability of an LLM later. Hopefully this was a useful talk for you. Thank you very much for joining me today. If you're interested in the kind of stuff that we're doing or in the boot camp, I would recommend you go to kono.io. And we have lots of good content coming out there, as well as a new workshop that we can do for your company. So thank you very much, and have a wonderful rest of the day.
Just Raul, quickly before we close out, we had one quick question. Are you seeing much action in the federated AI learning space?
So, yes, I've seen. So I'm going to interpret this in what I understand with federated AI, but basically federated AI, as I understand it, is that you have different types of AIs that are able to do different things, right? And what these LLMs do is basically allows you to have one system that can route your request to another system, right? Now, there's another aspect of federated learning or federated AI, which is where you train your models without necessarily somebody else, looking at your data. And I think that's in the realm of like companies like IBM and Google and Azure. I haven't necessarily seen that in the LLM stuff. but coming back to what I think about federated AI is you have a system, a general purpose model that understands what you are giving it, and it detects which system to use, and it can send a request to something else. But of course, I could be wrong. I'm generally focused on the LLM AI space and how that integrates with technologies, particularly existing models. So how does an LLM talk to a vision model, or how does an LLM talk to a text to image, or text to video, or can it understand what the video is? And you can definitely combine the two concepts, right? You can train certain models that you don't necessarily want them to have access to your data, but it's available to your company, it's available to your platform, and the LLM can basically use that particular model without having to give data to it. All right. Excellent. But thanks for the question. I appreciate it. And with that, we'll call it a wrap. See you guys next week. We're going to start doing these weekly. So see you soon.